Okay, I think we can just about get done with the exam review in this video, and then I'll post a little bit later some new material in the next set of videos. Let's finish up the review material. Okay. All right. So we just introduced the second law, substituted into an algebraic expression for state 1 to state 2. The next thing we talked about was kind of the mechanics of using the second law. Right? Well, there's three ways you can determine an entropy change. Three ways we can determine the entropy change. One is table properties. Okay? For water in R134A, our text has tables that what I need there is I need two properties. And we talked about all the possible combinations there, and all the different ways that works. Go back and review chapter 3 if you're still struggling with that. Okay? If you're in a different text, you might have other tables, but our text just has water in R134A, and other property tables would work the same way. Now, do not use S degree as S from the ideal gas tables. Now, the U and the H values in the ideal gas tables, you can use those. This, what I call S degree or S circle, is not the S value. These are not the same. Okay? We talked about, in a later video, we talked about the S degree 2 minus S degree 1 is equal to the integral of C sub P dt over T from T1 to T2. Okay? But it is not, these are not S's. This only accounts for the temperature portion of the entropy change for ideal gases. There's also the entropy change based on other properties we'll see later in the Gibbs equation. So water in R134, these are actual S values. You can use those out of the property tables. The S values in the ideal gas tables are not actually S values. They're part of the entropy change, but not the whole picture. So don't use those directly into the S values over here. Water in R134, you can plug those in right here. Use those as S values. That's just fine. The second thing we can do to determine delta S, we said, was the second law itself. All right? The second law itself will tell you the change in entropy if you can quantify the heat transfer as a function of temperature, and if you can quantify the entropy generated. Okay? So kind of the simple thing is, if S gen is known and or 0, okay? If you know you have a reversible situation, we already talked about, if you know it's reversible, if they've somehow communicated to you that you have a reversible process, you have the best possible version of this process, they've told you that it's not generating entropy, you can assume it's a reversible case, the best case. It's possible that they might also just give you a quantity for S gen that's a little less realistic, but not impossible. But anyway, right, it has to be a positive quantity or 0. Those are your options that are possible. If you compute S gen to be negative, that's impossible, and we just say, well, this process cannot exist. It doesn't make sense, or I've missed something, or I've converted my units wrong, which is entirely possible, or something like that. Done some algebra. Anyway, we could use the second law itself to determine delta S. That means I need to be able to quantify these two terms. The common thing, there's two things that can happen with this. Either this is what we're solving for, or it's a known quantity, and most likely if it's known, it's 0. Okay? The other thing is what do we do with this guy? What do we do with this crazy partial integral, Steve? Well, it's really just the sum of Qn over temperature is really what this represents. We're just saying you can break it down into every little differential slice of heat. That's why we write it as an integral, but it's really just the sum of Qn over T, where Q out would be negative. Now, there's two major things we can do with that. One is if it's adiabatic, it's well insulated, or they've told you that negligible heat transfer, and that's real simple. This integral of del Q over T, or dQ over T, just goes to 0. So if this is 0 and this is 0, then delta S is 0, and then we call it isentropic. Right? If both of these are 0, that means this is 0 and this is 0, then delta S is 0, or S2 is equal to S1. That's a special case we see a lot. Again, that's isentropic. But I need both. I need this to be 0 and this to be 0 for this to be 0. Okay? If that doesn't make sense, go back and review that. That's really important. I need both of these for it to be isentropic. There's a third scenario that we might encounter here, where we would use the second law itself to determine delta S. That's if we have heat transfer at a constant or average temperature. If you have heat transfer occurring at a constant temperature, then this integral of dQ over T becomes simply the sum of Q net in over the temperature at which it occurs. So what that means is that everywhere you've got heat, and we did this a second ago, right? A second ago we said, well, if you go around the heat engine, everywhere you've got heat going in, divided by the temperature at which it comes in. Everywhere, and subtract everywhere you've got heat going out, divided by the temperature at which it goes out. Right? We did this to a heat engine right? We said, hey, I've got heat coming in here at TH, so that's plus QH over TH. I've got heat out, QL going out, so that's minus QL divided by the temperature at which it goes out, divided by TL. Okay? Got too many devices in here all making sounds. I apologize. So unprofessional. Anyway, again, if you've got heat transfer occurring at a constant temperature, add in that heat coming in divided by the temperature, the absolute temperature, Kelvin or Rankine, at which it comes in. If it's heat going out, subtract it, divided by the absolute temperature at which it goes out. So that would be the surface of the device, the temperature of the surroundings. The surface of the device will be at the same temperature as the temperature of the surroundings at which it comes in contact. That we learned that in heat transfer, but you guys haven't got there yet. Okay, so those are the three possibilities to deal with the right-hand side of the second law. If I can quantify the right-hand side of the second law, that allows me to determine delta S. The third tool that I have for determining delta S is what we call the Gibbs equation. Right? The Gibbs equation, which in its rawest form is a differential equation, and we did some integration and substitution for two main scenarios. If we have a solid that remains a solid, or if we have a liquid that remains a liquid. And that's important because I'm going to use specific heats to determine that. These are little s's. These are entropy per unit mass. And again, because I'm using specific heat, if it's a solid, it has to stay a solid. And if it's a liquid, it has to stay a liquid. This is approximately, in our text, we use C sub P to describe solids and liquids. C sub P, natural log, T2 over T1. This is a C sub P average. If you have multiple C sub P's, take the C sub P at the average temperature, the average between T2 and T1. What else we got here? If it's an ideal gas. So if it's an ideal gas, there's multiple ways I can find this entropy change. The entropy change is approximately C sub V, average, ln, T2 over T1, plus R, ln, these are specific volumes, little v2 over little v1. Again, it's got to be an ideal gas. It stays an ideal gas. So don't use it with water in R134. It's just too likely to approach the saturation dome, and then this becomes garbage. S2 minus S1 can also be approximated with a C sub P average, ln T2 over T1, minus R ln P2 over P1. Okay? And you can, if you don't like using the specific heat at the average temperature, if I know the pressures, I can say that this is equal to S degree 2 minus S degree 1 minus R ln P2 over P1. This replaces this. This is an actual equal sign. These are table properties that I can pull out of the tables. This is an actual equal sign because these are exact values. This is an approximate value. Okay? So this is an approximation. This is an exact solution. Either way works, as we've seen. We saw in the examples, I can get just as good an answer using a good C sub P at the average temperature as I can using the exact S degree values. Take your pick. If you use these, you're probably going to have to interpolate. If you use this, you might have to guess and check. And either way is a perfectly fine way to get to a solution. Both are fair game to show up on the exam. If a problem shows up on the exam where you had to use Gibbs equation for an ideal gas, I would not force you to use one or the other. It would be completely up to you which method, whether you want to use guess and check to find C sub P. If you want to use the K ratios, if it happens to be an isentropic ideal gas and you want to use those K ratios, that's fine. Again, you will have to guess and check a K value if you don't know both temperatures. So any of those work. And if it's not isentropic, those equations don't help you. I'm trying to think if there's anything else that I've missed. I don't think so, guys. I think that is all of the theory associated with exam 3. There's a lot there, and without actually working through a good number of problems, if you just copied solutions from the internet to do your homework, you may really struggle with this exam. There's a lot of problem solving involved, and if you're just looking at solutions to problems, you're not actually practicing solving problems. So first thing you do, if it makes sense, you might write down the first law for the situation and then go ahead and write the second law. Unless it's a Chapter 6 problem. If it's a Chapter 6 problem, if it's a heat pump, refrigerator, or heat engine, if it's the entire device, then apply these principles from Chapter 6. Okay? Now, if you're just looking at, a lot of times the problem might say you've got a compressor within a refrigeration system, and it just gives you information about the compressor. That's not a refrigerator problem. If they're just giving you information about the compressor, that's a Chapter 7 problem. Okay? So the question becomes, have they given you the entire cycle, the entire device, or are they just giving you one element within the device? And we approach those differently. Okay, I think that's it, guys. I'm going to stop there. And like I said, I'll put out videos on the topic of isentropic efficiency. I'll put those out sometime Tuesday, and that's not on the exam 3, but that can show up on the final. All right, guys. Let me know if you have questions. Stay safe out there.